Here's a question that sounds abstract, but sits underneath almost everything in machine learning. When you fit a model, how does the training process actually decide which specific numbers to pick out of infinitely many possibilities? There is one elegant principle answering that. And the real surprise is how many familiar techniques you already use turn out to be the exact same idea, wearing different clothes. It is called maximum likelihood estimation, often shortened to MLE, and today we are unpacking what it really means to fit a model to data. Let us walk through the recipe because it is really just 4 steps once you see it laid out. Start with the fact that a model with some parameters assigns a probability to any dataset. Given a mean and variance, a Gaussian tells you how likely your observed points are, and the weights of a network do the same thing. Write down that probability of the data as a function of the parameters holding the data fixed. That function is what we call the likelihood. Then take the logarithm of it. This turns an ugly product of many probabilities into a friendly sum, and it behaves far better numerically. Maximizing the log gives the same answer as maximizing the original, so it is a free simplification. Next, find the parameter values that push that log likelihood as high as it will go, usually with an optimizer rather than by hand. Often you simply flip the sign and minimize the negative instead, which is exactly why negative log likelihood shows up everywhere as a loss function to drive down. Whatever parameters come out of that optimization are your maximum likelihood estimates. They are, by construction, the settings that make the data you actually observed as probable as the model can possibly make it. And a nice property is that as the data set grows, these estimates converge toward the true parameters. So why does this principle matter so much? Contrast it with the alternative. Without a principle, fitting a model feels arbitrary. You might tweak parameters by hand or reach for some ad hoc formula, with no clear reason why one setting should beat another and no honest way to justify the choice you land on to anyone else. With maximum likelihood, there is a single clean rule that removes the guesswork. Pick the parameters that make your observed data most probable and let the optimization do the rest. Beautifully, many familiar objectives turn out to be exactly this in disguise. So one simple principle quietly unifies a huge amount of what we already do every day. Let us hold on to 3 ideas that capture the whole thing. Maximize the likelihood of the observed data. That is the entire rule. Among all possible parameter settings, choose the one under which the data you actually saw was most probable to occur. Working in log space connects it to real training. Minimizing the negative log likelihood is a loss function, the very kind you already push down with gradient descent, which is why so much of optimization is quietly maximum likelihood running under a different name. This principle unifies methods you already know. Least squares is maximum likelihood under Gaussian noise. Cross-entropy is it for classification. And training a language model to predict the next token is maximizing the likelihood of the text. One idea, many familiar faces across statistics and deep learning. All right, for takeaways worth keeping. Maximum likelihood estimation picks the parameters that make your observed data most probable under the model you chose. In practice, you maximize the log likelihood, which turns products into sums, and minimizing its negative becomes a familiar loss function. Many objectives you already use are maximum likelihood in disguise, from least squares under Gaussian noise, to cross-entropy for classification, to next token language modeling, which is why the principle unifies so much of what we do. On small data, it can overfit, so priors and regularization step in through the maximum a posteriori view, or MAP. For more machine learning foundations made this clear and this concrete, visit standarity.com. See you in the next one.